I'm Anirudh Shah. I'm a research engineer at Iggy, and today I'll be talking about building better models with location data. So, quick overview of the talk. We'll start with like a use case, an example to couch the talk in, and we'll come back to this a few times. Then we'll give an overview of geospatial data and geospatial boundaries. Then we'll have a demo of how to use Iggy and geospatial data for like a use case, which is the example that we're giving in the first part. Then we'll talk about feature insights that we found through some internal modeling of our own. And finally, like a little sneak peek on graph machine learning with geospatial data, which is something we just started doing, but I'm very excited about. So firstly, this use case. We are building a vacation rental recommender system. And we have user data on previous rentals they visited and also some data about those rentals. And we want to recommend rentals for a user's upcoming trip to Austin. This person's on our site searching for Austin, and we have some profile data on them. They're in their mid-30s, and they're traveling with a group of friends. And we think that geospatial data will enable us to give better recommendations to them. So we want to integrate that data into our system. So firstly, what is geospatial data? At Iggy, we think of geospatial data as what is nearby. And this includes things like points of interest, which are bars, restaurants, museums, parking lots, schools, water bodies, socioeconomic data, park data, and much more. And for our use case, recommender system, the kind of features we may want to include are what are the nearby restaurants to each property, the nearby parks and recreation areas, rivers and lakes, etc. And so what data sets can be enriched with geospatial data? Any data with a location column, and this might be a latitude, longitude, address, zip code. And there are examples of this kind of data across industries: real estate, travel, marketing, public health. It's very flexible. And on the next few slides, I'll give some examples of some tables that can be enriched with geospatial data to give you some context. So first we have, this is city bike locations in Austin, like rental locations. As you can see, there's an address column, so we can enrich this with geospatial data. This is a data set about area deprivation index, which is a socioeconomic indicator. And again, we have a zip code column, so we can enrich it. And this data set is what we'll actually use in our demo, which is the vacation rentals. As you can see, each row is a different vacation rental, and we have a latitude, longitude. So again, we can enrich this with geospatial data. So why isn't geospatial data widely used in machine learning? It's difficult. And the key pain points that we have identified through our own experience and through talking to customers are around data engineering. So firstly, you have sourcing and acquisition, right? You may not be able to get good quality water data from the same place you can get good quality points of interest data. And because of this, you're analyzing and evaluating many different sources, aggregating them, and they may come in different formats. So that's one challenge. The other challenge is cleaning and quality checks, right? Sometimes the data is mislabeled. We've seen data that, because it had the word lucky in it, was labeled as a casino. But actually, lucky could be bar, restaurant, something else. So you have to go through and clean that kind of data. There might be missing data. So that's a challenge. Another challenge is computation normalization. Let's say you wanted to calculate catchment areas across the whole country based on the road networks. That's a lot of compute. And finally, engineering and delivery. You have to deliver this data in a form that's easily accessible for machine learning pipelines. And that's the non-trivial task as well. So next, we'll talk about geospatial boundaries. So to us at Iggy, a geospatial boundary is any geographic area over which data is aggregated. And you have administrative boundaries like a metro area, census block group, census tract, zip code, and then you have derived boundaries. And one that we think is very powerful is an isochrone 10-minute walk. What this is, it's a polygon around a location, and everything within that polygon is within 10 minutes walk of that location. And this is how we believe humans interact with their surrounding environment. Traditionally, in this kind of field, you did catchment areas based on a straight radius. As you can see in that image, as the crow fly radius, you might have a half-mile radius and a circle around the property. And this doesn't take into account whether you're crossing a river, going over a highway, that kind of thing. And so we think this loses some of the detail and the nuance in the area. This image is isochrones. As you can see, much more irregular, but much more natural in terms of how we think about space and movement. On the next few slides, I'll kind of give an example of why we think the isochrone is also a very powerful boundary for modeling and gives you more detail than a zip code census block group. So you'll be seeing some maps of Austin segmented by different boundaries and then shaded. And the shading will be the number of points of interest within that boundary. So this is downtown Austin, split into zip codes, and the shading tells you the number of points of interest within each zip code. Now the two white dots there are two properties that we're going to compare through this sort of walkthrough. And they're both in the same zip code. So if you aggregated at this boundary, they both have the same feature, and they would come out the same from this context. From a census block group context, it's better, they're smaller, so you get more nuance. But again, for our use case, these two properties are in the same census block group. So they have the same feature values. But now if you look at isochrone 10-minute walk, you start to see the nuance in how the city has been developed. The one to the east is closer to downtown. There's many more points of interest within a walking distance of that property. The one to the west is stuck between a highway, so it's pretty inaccessible. And so if you modeled it with using the isochrone boundaries, you can get this detail in your model and in your predictions. So now we'll do a little demo of how we use geospatial data Iggy and a use case around travel.
In this demo, we will demonstrate how to build a vacation rental recommender system, a very simple one, using Iggy and geospatial data. So the first step is to import some libraries, and then we'll load a rentals dataset, which will be a data frame where each row is a different property, and then there's some metadata associated with that property in the columns. So we load that, and then we load Iggy geospatial data, and then we enrich this rentals dataset with the geospatial data. And that's very easy to do. We've built this Python Iggy enrich package, and when we run this cell, we end up with this enriched data frame, which will be our vacation rental data frame enriched with the geospatial data. And that's what we use to do our analysis downstream. And so, as mentioned in the use case, our user that we're targeting here is someone in their mid-30s who's traveling with a group of friends, and that's the profile that we have. And so we have used our sort of domain knowledge to say users with that profile, there's some key features that they care about. For example, the number of CrossFit gyms within a 10-minute walk of that property, the number of restaurants per square kilometer, and the median age of the census block group that property is in. So we'll just subset this total enriched data frame on these features that we have selected. Next step is to filter the data further. This person has been searching for properties that accommodate 4 people, and they also would like to stay for 3 nights. So we need to filter our properties based on those criteria. Then we process and scale the data. And now we get to the recommendation part. As I mentioned, it's a very simple system. So we're just going to calculate similarities between different properties. And then we know that this person has visited Austin and stayed in this rental 409-56278 last year, and they gave it a great review. So we'll just select the 5 most similar rentals to this rental they've already stayed in, and that's what we'll recommend to them. So we calculate similarities, we select the top 5 most similar rentals, and we end up with this data frame of the original rental from last year and the 5 most similar rentals based on the features that we selected and the vacation rental metadata. And now we'll just plot this on a map so we can visualize it better. As you can see, we end up with this map where of Austin, the vacation rental that they stayed in last year is down here, and then 4 of the 5 recommended ones are also close by. And then we have this other one up here to the north, which is also recommended to the user. And if we zoom in, based on the features we selected in terms of CrossFit gyms, restaurants, etc., it makes sense that we're close to downtown. And 4 of the 5 are quite close to each other. And the 4 of the 5 are also very close to the rental of interest. So The visualization gave us a quick gut check on our recommendation system, and it seems to make sense.
May have been a bit small, but that demo is also available on our website if you wanted to go play around with the notebook yourself. So now we'll just talk about some feature insights. We've done some internal modeling with our data for different use cases around real estate and travel. And we found some interesting things when you incorporate geospatial data into these kind of tasks. So in the real estate realm, the use case here is we're predicting sales price for properties. And our data is property metadata, and then that's going to be enriched with geospatial data. And we saw a 2% lift in test set performance with geospatial features. And this is, we could have tuned it further. We may see different performance with different models, but this is sort of one result that we found. And the key geospatial features that showed up in our analysis were things like whether a coast intersects with a 10-minute ice screen around a property, the number of education centers, the number of gyms, and then a negative impact, which was the number of manufacturing facilities within that 10-minute radius, which makes sense. And the key property features, again, this makes sense intuitively: square footage, the floor finish, and the interior finish. So this is kind of insights into the key features in this particular task. And finally, this is a little sneak preview, like I said, of something that I'm very excited about: graph machine learning on geospatial data. So there are many ways to represent this tabular geospatial data graphically. This is one example that we've started playing with. So in the middle, in the node here, 19103 is a zip code in Philadelphia, and the nodes with edges to this middle node are the names of points of interest: CVS, Chipotle, etc. And then each of these names of points of interest have another node with an edge to it, which is the POI type: restaurant, pharmacy, grocery store. And so this is one way of representing that tabular data and representing the relationships between different entities. And how might we use these graphical forms? The first way we're thinking about is quality control. We ingest this data and it's already tagged by the POI type. And sometimes it's incorrect, as I mentioned in the challenges with geospatial data. So we could build a node classification model on top of this representation to predict the POI type for each of the POIs in a data set. And it will show up, where is the discrepancy between the incoming label and what we predict. Another thing that we're playing around with is representation learning. One use case here is you could embed this zip code based on the POIs in the zip code and then compare embeddings between different zip codes. Let's say you wanted to recommend a zip code that someone should move to based on where they currently live. You could do that. So that's representation learning. And finally, this is such a flexible form of data that we can incorporate other data types in: satellite imagery, text, it could be reviews of the business, and these could be node features. And then again, we could go back and do quality control, representation learning with those new features. That's all I had. Thank you for listening, and welcome any questions at the end. Thank you.